Welcome to our second demo day. And today with me is Dominic, who runs engineering. And we're going to talk about quick Tenzir intro, some high-level use cases. Then we're going to move into the topic of today's session, which is parsing and decomposing complex structured layered data. And then we'll also give a demo about how you can enrich data flows with the new contextualization framework that we released with Tenzir 4.6. Okay, just a brief intro about Tenzir when you would use it. Briefly, we have 4 use cases. One is optimizing SIM cost. You can basically put Tenzir between your data sources and your data sinks, shave off some costs. You can use Tenzir to run your detection content. And with detection, we mean everything in the spectrum of a single point IOC to a Sigma rule, to a Python script, to a ML model. There's on the right side, we have 2 infrastructure topics, building a security data lake. Tenzir can be your ETL layer to move the data into the lake, to standardize it, normalize it, and reshape it. And the bottom right use case is complementary, which is building more of a distributed system, the data fabric, for example, where you keep independent islands of data, but somehow want to manage them centrally and run queries across them centrally and run pipelines decentrally. There's a in-depth, in the documentation, we have more examples. All of these use cases are written out. If you just go to docs.tenzir.com, you have a wall of text with each of these associated, but we'll just wanted to mention it briefly here. So what are the moving parts for Tenzir? Is centered around pipelines. Pipeline, you can run a pipeline in isolation on the command line by using the Tenzir binary, and then you specify as a string the pipeline itself. But that's just the low-level interface. You can run multiple pipelines within a node. A node gives you a managed set of pipelines plus optional storage as an abstraction. And the node can be interacted with through an API, or again, with the command line. The node also can connect itself to our platform, which Dominic will show you in a second, and also throughout this demo, we'll use app.tenzir.com, and that provides a graphical user interface. And but it's important to understand that all the pipelines and all the storage are within the node that you are deploying in your infrastructure, and the platform is really just an access path and management layer. Okay, so these are the high-level moving parts of Tenzir, and now we're going into the first demo. And to recap on how data acquisition works in Tenzir, you have to remember a pipeline is basically a sequence of operators with a source in the beginning that has as a side effect acquiring the data, then it gets transformed, and it must end in a sink to be closed and able to execute. So one example here, what we see is basically we see a source operator, and there's one instance which we're going to use also in the example is we're loading data from a TCP socket and we're parsing it as Syslog. This is an example of the data acquisition framework where we separate the acquisition of bytes through the connector API. And here we have a loader that then sends bytes to the parser. And the parser is the element that transforms the bytes into structured events. Then you can do a bunch of computation on the events, and you go out in reverse order. You take the structured data and turn it with a printer into unstructured data before it gets saved somewhere. So that is basically what we have for data acquisition and the inverse. And I think from here, I would give the screen to Dominic.
Hello. All right. So I will take over the screen share, and you should see the Tenzir app right now. So I'm here on app.tenzir.com, and we will build this up incrementally. So we will start with a very simple example. So I have locally a file called syslog.log, and that contains some syslog. So this is very close to the pipeline that Matthias has shown you. I can press run for this, and you will see that this structurally parse the syslog that is in my file. And well, there's a problem here. So you can see what's very common with syslog is that the message field is usually in some other format. So there is no one standard where you could say, okay, we are parsing syslog, but rather you have something nested in there. That could be Ceph. In this case, it's JSON. So what we want to do is we want to now again parse the JSON that's inside the message field. So we can do this. We just add an operator with a pipe symbol. So we do pipe to parse, and we parse the message field as JSON. And when I hit run again, what you will see for the same output is that suddenly here, instead of a string, I get a record. And I get a record that contains two fields, those who are in the JSON originally. And in particular, these contain a request string and Matthias.
One question, Dominic, can you show us the vertical representation of this?
Yes.
Thank you.
Great.
I think that makes it a bit clearer also when you want to say copy and paste it or see the structure of a single event.
I can do that, yeah. So now for further destructuring this, what we want to do is take a look at how we can further decompose the request and the date fields. So for request, what we have here is some IP address followed by a string, like an HTTP action, and then a URI request parameter. And what's very handy for this is utilizing Grok. So Grok may be known from other tools that support acquiring data and doing this destructuring. So it's a very common framework. And we basically support Grok out of the box. So you can apply the Grok parser to this message.request field. And the way that we're doing this here is that we're saying, okay, we have three individual space-separated fields. We have an IP address that corresponds to the field name client. We have a word, and that corresponds to method. And then we have a URI path param, and that corresponds to the field request. So when I execute this, and I again take a look at my data, what you will see is that I again have something nested here. So now I have a message.request of client, method, and request. And I have this now further split out. Now for date, it gets a bit more complicated. Dates can arrive in like various shapes and forms. And luckily there is like one de facto standard library for date parsing that everyone uses, and it's in Python. So how would I do that? And the answer is really quite simple. So what I can do is I can write the Python operator. So the Python operator lets me modify events one by one. So I can just say, okay, I am using date_parser and its parse function. And for the date field, I will just replace that with the parse version of itself. So when I run this, what I get is now actually a correctly parsed timestamp. And you will see that this field now also has the type time. So I can do all sorts of time operations with it. So I'm very close to now having like parsed this syslog in a way that I want to work with it. One last thing that I may want to do is maybe only take a look at a subset of the field. So right now, not everything that's in here is relevant to me. So maybe what I want to care about is like precisely this date, and I want to call it timestamp. I maybe also care about the host name and about the process ID, and then I care about this request, but I don't actually care about the auto framing. So I can do this with put. I just rearrange my data as I see fit. And what I end up getting is precisely this in a very useful form. So now I have done this with my syslog, and this was obviously just a one-off example. So what we want to do now is we actually want to acquire the syslog from where we usually get it. So in this case, we just say, okay, where do we read this from? Let's maybe just read it from TCP, and usually that's something like localhost. I think port 514 is what we have configured on most of our machines. And then what we want to end up doing is we want to import this. So this now is something that we can continuously run. We get prompted, okay, we can create our pipeline, and we could just say, okay, this is our HTTP log over syslog, or however we want to call it. Maybe we actually don't want this to ever like stop, even if there's a failure. So we say, okay, when it's like failed, restart it automatically. We can create it, and we can see immediately that this is running. It's starting to do things. All right, here it is, and I can now assign it some label to make this like categorized. But this is now running continuously. It's doing things in the background, and I can stop worrying about it. So this is how I now have onboarded data in one example. All right, handing the mic back to Matthias. Any questions?
Yeah, also to the audience, if there's any questions, now is a good time to bring up any questions. We can answer them in line. If not, I will take over the screen and we'll go into the second example. And what we've seen right now, to recap, is a reshaping operation. Yeah, there's actually a question from the audience. Great. So this is about import. And let's go back maybe to this slide. Import is a sync operator. And if you may have seen that the initial prototyping and reshaping of the data basically ended always with a transformation. And that's because we are looking at the data through the browser, and we autocomplete, so to say, the sync to mean that you're looking at it in the browser that's running in the pipeline. So you were not, and once you've added explicitly a sync to your pipeline, and we had import as an example, then the pipeline is fully complete. We deployed it, and import, what it does, it stores the data at the node. So also going back further here, every node has storage, and this is either Feather or configurably Parquet storage. And when you end a pipeline in import, it stores the data at the local node storage. You can, when you're running in a Docker container, you can mount in the storage on a file system. And we have also plans to support native remote storage like S3. Does that answer the question? Awesome. Okay. Then let's move to the next demo. So with the last release, we added a new contextualization framework. And what we mean with contextualization is that there is some state, and we're calling it context. And you basically have this in-band mode of contextualization. Contextualization, aka enrichment, maybe enrichment is a better word for using the data from a context. But in a typical way is that you're in a low volume case, you get by with doing API calls. And that's probably the most common way of the way people think about enrichment, by just calling a bunch of remote APIs and attaching more data to your pipeline. And I think that works. And we also have, when we're going high volume, and by high volume, we work a lot with Suricata and Zeek data, that can reach up to 100,000 events per second. And then doing one API call per event is maybe no longer possible. So, and also if you're running maybe off the internet, it's also, that's like not possible in the first place. It's interesting that Google's Chrome browser does a middle ground where they use partial context, and if that's a probabilistic data structure, and if that actually yields a hit, then it does a full candidate check for bad URLs, for example. It chops up the URL in a variety of different ways, and it performs then a local offline match, and if there's one of them matches but they're not sure, then they do an API call. So what we are going to show today is this mode of contextualization, the in-band for high velocity data. And for that, we have built a framework that has this notion of state pluggable. And we call it the context. The context is the stateful object, and it exists in multiple types. We have, today, we're going to take a look at the lookup table. which is probably the way most people think of enrichment and think of contextualization. They do basically the equivalent of a join at a specific key, but in real time as data flows through something. And the other one that's pretty common is GeoIP. You can model that as a table, but there's also libmaxmind as its own database, and you can it has reading that often, and integrating that is another way. And so we have built a custom plugin for it, and by simply deriving from a C++ class. And you can roll your own context type. Whenever you have some state that on the one hand wants to be managed, updated, and we'll show an example with threat intelligence in a second, and you want to enrich with that context from the other side. So there's two sides of it. You use the context in one or more pipelines through the enrich operator, and you manage the context with some either statically with the configuration file or with these operators. And this is not, the Bloom filter context is still in the works, and that's just a more space efficient representation of a lookup table, where you basically get a Boolean yes, no, if a certain key is in there. So if you have billions of IOCs and you're running and you have a limited amount of memory, that would be a good way to say distribute that. We have that scenario in a different context. So the Bloom filter is coming up next. Okay, that was it. Dominic, feel free to show us how this works. You're still muted.
All right, thank you. So back to my screen. As Matthias said, contexts. So contexts, I have a two-step or sometimes a three-step process to using them. So what we first want to do is we want to create a context. And the first context type I want to show you is the GeoIP context. So what you do is you run context create, and you give your context a name. So in my particular case, I will name this one countries, and it is of the type GeoIP. And for that specifically, and that's something you can then look in the documentation, is you need to put in a path to your libmaxmind database. Right now, that's still a manual process. In the future, we also want to download that by default. But I have one here locally, and that's called geoli2 country.mmdb. So I can create this, I can run this pipeline, and you will see, okay, I actually got this one back. So now I can use it. So let us actually take a look at some example data. And Matthias mentioned high volume data, and one example for that is Suricata. So I have, for testing purposes, a Z-standard compressed ETH.json file here that I can read from, and this contains a bunch of different Suricata events. So one operator we can use to just get an overview is taste. What taste does, it just makes it so that I get at most as many as specified from every event that's in there. So you can see a distribution in this entire ETH.json file. I have these different schemas present. So I don't just have flow logs, I also have HTTP, alert, and so on. And there's one thing here where having a GeoIP is really interesting, or actually two. Specifically, almost every Suricata event, I think except for the stats event, contains source IP and destination IP fields. So it would be quite handy to be able to enrich this flexibly across all schemas. And I can do this. So the way that I do that is I specify enrich. And for enrich, what I need to do is I need to say which context do I want to use. I named mine countries, and now I need to say, okay, for which field do we actually want to do this? So let's start with source IP. So I can say, okay, apply the countries context to the source IP to the source IP field, and you see suddenly I have in here a countries field that contains the key that I matched, and then the context that is all the GeoIP data. So now let's give this a name. Let's maybe call this source country. And let's do the same thing all over again for destination IPs. So if I do this, now dest country for dest IP, so what I end up getting is source country and a destination country. I can expand this. I can show you the full thing here. This is a lot of data that I get out of my MaxMyDB. So let's say that the only thing that I'm actually interested in is this ISO code, because maybe I want to work with it further down the line, and most of the other data is maybe not so relevant. The key I already have in form of my source IP and dest IP, but maybe we just are looking for this ISO code. So what I can do is I can replace it. So I can do replacements. I can say my source country is actually just my source country.context.country.iso code, and I do the same thing for my dest country. And when I do this, I take a look at my data. I now, for every suricata event, have a source country and a destination country, and this works in real time across all the different schemas that I have in here. So again, if I now wanted to import this, I would say, let me maybe read from a socket. So I would say, okay, maybe have my eve.soc or so, or however my suricata is configured. I want to follow that file. And now again, I want to ship the resulting event somewhere. I could import it as my node. I could also ship it to Kafka. So maybe I have a Kafka topic, and I would just say, okay, write this to Kafka, and under the topic suricata, and use the format JSON and make it compact, right, in a single line, so that I can downstream subscribe to this with any suricata. We have a raised hand.
Yeah, thanks. So this is actually something we get asked quite a bit. You can see the language looks very similar to Splunk, but there's a lot more power in the ends of the pipeline, both in the way you get data into the pipeline and data get out. And if Dominic would just replace the first line from with export, it would be the equivalent of running a historical query over the data at the node. And what we're doing here right now is running as a source of the pipeline a local file. And so the from, in this case, showed the file. And at the other end, we have the same symmetry. Like when we exit the data in the pipeline, if we don't add a source, it arrives in the editor, the explorer that we're seeing here right now. But once we add a source, it's a closed data flow. And that one is something we can deploy and run at the node continuously. So just wanted to add that because that's kind of implicit in the language. And it's basically that difference to the other systems. Dominic, yeah, thanks.
Right. Yeah, moving on to the second example. So the second example for context is the lookup table. And the lookup table is just a mapping from one key column to a context. And that context can really be anything. It can be any data. It could itself be a record, some structured data, or it could also just be some individual values that you want to put in there. So let's create a context, and we will call this one ThreadFox. And ThreadFox may be a service that some of you know. It's here, I say context create, I pass in the name of my context again, and I continue with the type. So I say, okay, ThreadFox is a lookup table. And unlike for the GeoIP, I did not put in like some database directory. Instead, for the lookup table, the state is managed very dynamically. So let's take a look at ThreadFox, which has an API that is really interesting to us. So I can query ThreadFox API directly from within the pipeline. So we have a very convenient syntax to this. I can just say, okay, like get this like from this API endpoint, put in these parameters. So it will get every IOC for the last day. And I can run this, and depending on my internet speed, I get something back. So you see, okay, it says query status okay. I get back some data list of record here that contains a lot of entries. And this is not something that we can very nicely work with. Instead, what we want to do is we want to just take a look at the individual entries that we have in data here. So there's an operator for this, and that's called yield. And with yield, we can say drop everything that is like in this outer framing and return me everything in the data array as its own event. So we can do this and we get this back. So you can see we have a bunch of indicators here. And now we may want to filter this a bit. So for these indicators, all of them have a certain IOC type specified. And I would like to, for now, just focus on the IOC type called domain. So again, I can run this and you will see a filtered list here. So you can see now everything that I have in IOC type contains domains, and I have certain IOCs here that are all domains that I could match against. So I would want to add these to my lookup table using the IOC column as a key. So now I can just say context update, and I will update my ThreadFox context. And the key column that I want to use is called IOC. So I do this, I press run, and I see, okay, I added a total of 25 entries to my ThreadFox lookup table. And now I can use it. And the good thing is these updates and using it, that can happen concurrently. So I can continuously feed information into this lookup table, and at the same time use it from any number of other pipelines. So going back to what we had earlier, so just taking the same example again that we had here. So we have our if JSON. I think I added a taste 5 here to just get a little bit of everything. So what we can do now is we can take a look at some events where we want to evaluate this. So one example here is HTTP. And for HTTP, we have this hostname field. And that sometimes contains also domain names here. It's a good mix of IP addresses and domain names. So we want to match http.hostname against this lookup table. So again, we use the enrich operator. We specify the context we want to use, and we say, okay, the field that we want to do this lookup for in our lookup table is called http.hostname. And we can run this, and it will, for every single event, whether there is an HTTP hostname or not, add a ThreadFox field to the output. So you can see for alert, there is no HTTP hostname, so it couldn't add anything. But for HTTP specifically, you will see that there is a event here that actually matched. So here we have ThreadFox as a record, and you can now have this in line. So I have, for this HTTP hostname that I had in here, my ThreadFox context that I enriched the event with. And I can see the key that matched. I can see the entire context. So this is the entire entry from the ThreadFox list. And I can also see the timestamp at which I matched. So this would, again, be another enrichment that I can do and that I can flexibly deploy. And I could now reshape the data with the same mechanisms that I used for the other pipelines. Yeah, Matthias, handing the mic back to you. Any questions?
Yeah, so maybe just a quick recap what happened. We basically saw how Dominic used the lookup table, the ThreadFox example, and also used the geo IP context, which internally uses libmaxmindDB. So there are two different plugins of a context. And we saw how you can manage the context on the one hand side with the update operator. And we saw also how you can use it with enrich. Yeah, so that's it for today. I think we went through this in a good speed. The recording will be made available. You can try this out yourself on app.tenzir.com, and our documentation at docs.tenzir.com. They have a lot of useful material. Like I said, the use cases are elaborated on quite a bit more than I had time here in this webinar. And make sure you look at our blog. Subscribe to it, because there's also a lot of good examples. We have a long blog post on how the contextualization that Dominic showed is taken one by one. And with that, yeah, if there's no further questions.
There are, Matthias.
Oh, yes.
There is a question in the chat. Can I use the context with emerging thread pro or MISP?
That's a great question. In theory, as you could see, as long as the data is accessible from a pipeline, you can use it and put it in a lookup table context. And arguably, the emerging threat data can be represented that way as well. For MISP, it's quite interesting. We are actually with Alexandra and Andras, who are running the project. We have a next year with them an effort where we're precisely doing that, building a MISP context so that you can think of MISP as an opaque thing and don't have to, say, manually attach to the 0MQ export that it has, or use the API to continuously pull into it. I think today you would simply use the MISP API and periodically run context update with the subset of MISP events that you're interested in. Maybe those with the IOC flag set. And then these attributes you would basically in the pipeline use and pipe them to context update. And that's the way you would do it today. And I think moving forward, it will be something like where you create yourself a MISP context and it's handled for you. Okay. So then there's another question in the chat, and it's about what's the story behind hot/cold storage of lookup tables. So lookup tables are always in memory. There's not a persistent approach to them yet. I think the idea is, and the idea is if you have so much data that you want to, I don't know, if you exceed the RAM, basically, there's two approaches. One is maybe switching to a Bloom filter if you want to have billions of smaller points, and then you can still use that at high velocity for enrichment. But if you actually need a key value mapping, a Bloom filter is not going to cut it because it just gives you a yes/no. And so you basically need to encode every information in that very Bloom filter to get to the data that you want. But if you want to have a lookup key value pair, then it would be difficult to do. There's another approach. We could, for example, add a Redis context so that and Redis does very fast key lookup operations. So that is the other option. It's kind of separate from this discussion of how do you join data. So because the idea is that this is a very stateful thing that you would always use a context when you have state that changes and you want to manage state in some fashion. That's the abstraction, so that you can update it in one way or even update the same context from multiple pipelines, but decouple it from the use. Hope that answers the question. Okay. Great. So thanks everybody for showing up. We'll have recorded this so we can post it later on YouTube. And looking forward to see you next time. All right. So one more thing, just to make sure everybody has also visibility of what we had in the chat. The idea was basically accidentally hitting paid API enrichments. Yeah. So that is basically going back to what we had here, where you do API calls. These can be incredibly expensive and quickly hit the limits for high volume. And yeah, the only option is really to go either this way or this way to reduce yourself. And that needs to be architected in the system, and you need to have at least a subset of the data to run in band. So yeah, exactly spot on, which is also a problem we encounter a lot. And fortunately, though, for a lot of enrichment data sources, you can get access to the raw data. And that's what we're using here. Okay, this is it, and see you next time.